to evaluate this directly. So this is something that comes up is where you have a closing surface composed of a couple of pieces, and we integrate over the solid in between. Now this is particularly useful if the divergence of f is equal to 0. So immediately we have to evaluate this. In other words, you can replace in that case, you could replace a difficult surface integral with an easier one.
0 factorial is 0, right?
Fine. That's why I try not to do that, because someone's going to point that out. But yeah.
Point. Isn't 0 factorial actually accepted to be 1?
Yes, that's why I tend not to, even if I want to use the exclamation point to make a point, I think, oh, I have 0 here, and it's be 0 factorial, and someone's going to point out, hey, that's 1. And yeah. Okay. So that's when this idea is particularly nice. If this wasn't very hard to evaluate, but if you don't have to evaluate it at all, well, that's even better. So what you have here is if you have one surface that's your difficult surface, and then your easy surface to integrate over, you combine them together to form a region, and if the divergence of your particular vector field is 0, and you're within that region, then you can just integrate over this, and it'll up to a sign. So minus the integral over this surface will be equal to the integral over this surface. All right. So that is the idea that we used here. Is just that this integral didn't go away; it was just easier to do. All right. Okay. So when you're parametrizing your surfaces, go ahead and compute the normal vector. Make sure it's pointing in the right direction before you proceed. Now, bless you. Of course, one thing to keep in mind is what happens if you get the orientation wrong. How does that affect the sign of the integral when it's all said and done? Yeah. So as long as you know to do that, then you can just keep that in mind. Because if you really don't want to bother trying a different parameterization, as long as you know that your orientation is wrong and you got to flip the sign of the integral, then you can do that. All right. Okay. So you still need to check. All right. Now, during the last 9 minutes, one other application of the divergence theorem goes to conservation of energy. Okay. So in this case, we're going to assume that F, the vector field, represents flow rate. So rate of flow with respect to time of heat energy. So that means it's equal to minus constant, a positive constant, K, times the gradient of T, where T is temperature, and K is thermal conductivity. This is known as Fourier's law. Okay. But Fourier was quite a mathematician. A lot of things are named after him. Now, So the basic principle of conservation of energy is this, that if you have solid E, bounding surface S, bless you, that the rate of change in respect to time of the amount of heat energy inside the solid is equal to the flux flow across the surface into the solid of heat energy. All right, so on both sides of the equation we have rate of change with respect to time, because that's what the flow rate is. So the total accumulation inside E is balanced out by the amount of heat, the net amount of heat flowing in. Because heat energy could be coming in, could be coming out. So all told, the net flow into the solid is equal to the rate of change of the amount of heat inside. And we gotta say into the solid, because if we're getting more heat energy inside, then this rate of change is going to be positive. It's going to be increasing. So we want that to match with this sign, the flow rate across the surface, and that's why we say into the solid as opposed to outward flow. Okay, now if we express all of this in terms of integrals, here we have rate change with respect to time, a triple integral over the solid of rho, which is energy density, dV. And then on the right side, we're going to have a surface integral over S, and we're going to have our vector field F, dot product with minus n. Yes. Why minus?
Didn't you say it was heading into the object?
Yes. So, but typically the unit normal vector is pointing out, so we negate it, so it points in. So that's the only reason I'm doing that. Okay, now, rho, we can relate to the temperature as well. So it's equal to C rho naught T. C is specific heat. Rho is the density of the medium, so the material that we're dealing with. And we'll assume that this density is constant. So it's a homogeneous material. And then T is temperature again. Okay, so now what we can do is say that the triple integral over E of specific heat, density, and the rate change with respect to time is equal to minus surface integral of your vector field, which is K delta T, but we have another minus. So we have a minus from a normal, and then we have a minus from a definition of F. Those will cancel out. And this is what you're left with. So over S. So it's conservation of energy, and keep in mind how the flow rate and the energy density are defined in terms of a temperature. So now we have temperature on both sides of this. This is the only variable in question. Really, everything else is a constant. Now,